Gonna start chapter 2 from today. So this chapter is about elastic behavior or Hooke's law. So in this chapter, we will talk about stresses and strains and elongations. We'll also draw a normal stress and normal strain curve. We'll talk about Poisson ratio and Hooke's law. And after discussing these topics, we will do some calculations. So I don't know how many of you guys have taken the material. Uh, okay, but not so many, right? Yeah. So it's gonna be for you guys maybe a revision, but for others, I think like these stress concept and strain concepts and elongation. I think these are newer topics for the rest of the class. So I'm gonna like review them. So remember last time in the first chapter we were talking about mechanics of material. That mechanics of material is actually a branch of deformable body mechanics. So whenever the forces are applied on the member is actually gonna deform. It's gonna change in shape, which we were ignoring the last time. So for example, if there is a member and if you have applied a force to that member, so this member will actually change shape. So it's gonna stretch out a little bit. So whenever you apply a force, so in this case we are applying a tensile force. So whenever you will apply a tensile force, you're gonna see stretching in the member as well. So we also need to be aware of these things, and we also have to calculate how much is the stretching and what happens when you apply a force. So for example, if you apply a compressive force, so member will reduce. So this was the original length, but when you apply a force, the member will compress a little bit. So you will also see changes in shape. So in this chapter, we will talk about two fundamental concepts. One is called stress and another is called strain. So we'll talk about stresses, how we can calculate stresses, what are the equations for strains, and then after calculating stresses and strains, we're going to draw a stress strain curve, and I will explain you guys why we need to draw a stress strain curve and what's the importance of this. And then we'll talk about Poisson ratio and Hooke's law. So let's start with stress. So in order to explain stress, we have in the workbook also you have this picture. This is a picture of Roman columns, and it's located in Switzerland, and it's a very nice location. You have Lake Geneva, like there also, and also you have the Alps mountains. So in this neon, this Roman column, it was built basically 50 AD, but it's like part of that structure is still there, and you guys can see. So the total length of this remaining structure is about 7.5 meter. So what we will do is that we'll do idealization of this Roman column. So let's try to do the idealization for this column. So I have drawn the idealization of this column as here. So we can see this part is kind of fixed on its footing. So we can reasonably assume that the base is a fixed support, and we can also calculate the external force. So how we can calculate the external force is basically this part, the weight of this part, half of the weight will go here and half of the weight will go here, and we can calculate the weight of this part basically if you know the mass and if you know the gravity, which is 9.8 meter per second square. Mass you can calculate. If you know the density, if you know the volume, you can calculate the mass. So basically you can, so this weight is actually a force. So half, if you calculate the mass of half of this massive limestone uh, member, you can calculate the force. So you have and we can do the idealization of this part as an external force. So we know this is a Roman column, and we have done the idealization of this one of the Roman column. So we can calculate the external force by calculating the weight of this limestone. By equilibrium equations, we can also calculate the reactions. And if you cut a section, you can also expose the internal forces, and you can also calculate the internal forces as we were doing in chapter 1. So now what I'm going to do is that I'm going to expand this part, and I'm gonna make it bigger for you guys. So if you make it bigger, that's how it looks like. So what is this is basically, this is the part of the neon column, and we can calculate the weight, so we can calculate the force. We can also cut a section, so we can expose the internal forces. So this part is basically, I have like enlarged and shown here. So this is basically half of the column. I'm showing this just because I want to like explain what's happening with the internal force. So we know this is external force. We can calculate the reactions. We can also calculate the internal force using equilibrium equation. So this is the internal force. But actually, this internal force, something looks like this. So before, what you were calculating was the resultant force. But actually, in the member, if you cut a section, this is resultant force is actually distributed along the entire area. So basically, the external force is being resisted internally by these distributed forces. So if I want to draw a 3-dimension, so these forces are actually uniformly distributed forces, not one force, but when we calculate, we just calculated the internal force as a final resultant. So that's what actually happened. So there are like all the forces along that surface area. But if you add all those forces together, you're gonna get a total resultant force, which you guys calculated before. So it's more intuitive to talk about this internal force in terms of area. So basically, you have to calculate the internal force with respect to area. So if you divide this internal force by the entire area, the thing which comes out is called stress. So stress is basically the internal force divided by the cross-sectional area. So that's the formula for internal stress. It's super important, and we're gonna use this formula in the equation, in the calculations all the time. And it can be numerically represented by this equation. So this is called sigma, and stress is whenever you have a force, you divide by the cross-sectional area where the force is acting, and force per unit area is called stress. And there are two ways you can visualize stress. One of the way which I've shown you here is called macro scale or average stress approach. So this is the first approach where you can calculate stress. So in this approach, how you calculated stress is that you have a member, which is in this case, maybe let's just say this is, and there's a force which is being applied to that member, and we know the area over which the external force is being applied. So the stress would be the force over area. So whenever someone asks you, like, you are given a force which you can calculate by equilibrium equations, you know the area, you divide force by the area, and then you can calculate stress. And this method of calculating stress is called macro scale or average stress. There's another method uh, of visualizing stress, which is called the micro scale approach. So in this approach, what we do is that we take a very small particle, and then we zoom out and we see what's happening in that particular particle, and then we can like sum all the particles together, and then we can calculate the stress as well. So if I zoom this very small particle, I can zoom out, and this will look like a cube, and we'll call this cube stress element. So of course, on this stress element, part of this external force is acting, and this is the entire area, and the area for this is part of that area, differential. So if you divide this force by area, you can calculate stress in this way as well. It's basically a different way of looking at the stress, but the formula is the same. So the formula is force divided by area. So there are two methods. One is macro scale approach, where you just see overall force and overall cross-sectional area, and you divide the force with the area and you calculate the stress. And another method is macro scale approach. It's very useful, and we'll see in later chapters like how it's useful. But another way is micro scale, where you just take a very small stress element and you zoom out, and that's the stress element, and you can basically visualize all kind of forces on that stress element. But for now, you can calculate the stress by using this force and this area. So stress would be part of the force, part of the area. But basically the formula is same. The formula for stress is force divided by area. So what's the definition of force? So the force is defined as force over an area. So you've already been calculating forces before, and if you know the cross-sectional area, you can calculate the stress. But the stresses are basically of two types, and the type is defined based on the orientation of force and area. So there are two types of stresses. You have normal stress, you have shear stress. So this is coordinate system. Let's just say x-axis is positive in this direction, y-axis is positive in this direction, and z-axis is positive outside the plane. So if this is x-axis, this area which is perpendicular to the x-axis, this area would be called as x area. And this is y-axis. So the area which is perpendicular to the y-axis is called y area. And this is z-axis. This is z-axis. So the area which is perpendicular to the z-axis is called z area. And if this is x-axis, this is y-axis, this is z-axis, the force which is acting along the direction of x-axis is called f of x. The force which is acting along the y-axis is called f of y. The force which is acting along z-axis is called f of z. That's the conventions which we were using before as well. So what is the difference between a normal stress and a shear stress? The difference is based on either the force is acting perpendicular to the area or the force is acting parallel to the area. So if you look in this example, this is x area, and the force is acting perpendicular to the area. Perpendicular means 90-degree angle. So if the force is acting perpendicular to a given area, which is the force is making a 90-degree angle with the surface of the area, then this type of force is called normal force. But so let's just talk about this area. This area is along y-axis, so we'll call it y area. And this force is acting along x-axis, so we'll call it f of x. So we can see in this example that the force is acting parallel to the area. So the force is making an angle 0 or 180 degree with the area. So whenever the force is acting parallel to the area, then this type of force is called shear force. So basically, shear stress. Basically, stresses are of two types. You have a normal stress and you have shear stress. So you will have internal forces, and because of the internal forces, you're going to have two types of stresses: normal stress and the shear stress. So if I draw the uh, column, neon column, which I drew before, so this is the area, right? Cross-sectional area. If the force is acting perpendicular to the area, which is the force is making 90-degree angle with the area of concern, then this type of force is called normal force, normal stress. And if the force is acting parallel to the surface area, which is it is making 0-degree angle with the surface, then this type of force will cause a stress, and the stress is called shear stress. So that's the two type of stresses based on the orientation of a force. And these are the formula for the stresses. So the formula for normal stress is force divided by area, but and we can call it sigma, the symbol. And for the shear stress, we can call this tau, it's a Greek letter, and that's the formula for shear stress. So basically it's like stress is force divided by area, but it depends on like either the force is acting perpendicular to the area or the force is acting parallel to the area. If the force is acting perpendicular to the area, then that's a normal stress. If the force is acting parallel to the area, then that's called shear stress. The stress which will be caused because of the force which is acting parallel to the surface area. So this is also stress element. This is also stress element. Now we're gonna see the total, like how many like type of force stresses are acting on a stress element. So this is a stress element, and we can see that on a stress element there are basically 6 sides, but 3 sides are more important: this side, and this side, because the other 3 sides are also like almost the same but opposite. So if you talk about a stress element, on a stress element there are possible 9 type of stresses which can act on a stress element. 3 types are normal stresses, and then the remaining 6 types are shear stresses. And when we will do the calculation, it's gonna get like clear, but for now I'm just explaining that there are like different type of stresses on a stress element. So and you can also figure out like either the stress is normal or shear. So for example, if you talk about this stress is acting perpendicular to this area. So this stress is kind of making 90-degree angle with the surface area, this force. So you can see this force is a normal force. Similarly, this force is also a normal force because this force is acting perpendicular to this area. So this is also a normal stress. And this stress Z, is also a normal stress. And the formula for stress Z would be the force acting on the Z direction and the area of Z. And this stress, this one, these all are shear stresses because all these forces are acting parallel to the surface areas. So if I ask you to calculate stress Z, for example, so you will, if I give you a stress element, and I give you forces, let's just say I give you 10, this is 20, this is 30. If I ask you, and if this is x-axis, y-axis, and z-axis, if I ask you what is the stress z, so that would be 30 divided by area of z. So this is the AZ. So similarly, you can calculate the shear stresses as well on the face of a stress element. And you can also see, if you want to calculate stress X, you're going to divide by area at X and the force X. If you want to calculate stress Z, you're going to use force Z and area also along the Z axis. But if you want to calculate a shear stress, so shear stresses are acting, the forces are on another surface and the area is another. So how it works is that the first subscript is basically an area and the second subscript is basically a force. So if I ask you to calculate stress xz, uh, this is x, so you will use ax. This is z, so you will use force fz. So that's the convention. But when we'll do the calculation, it's going to get clear. But for now, all you need to know is that on a stress element, you have 3 normal stresses and you have 6 type of shear stresses. Now, let's talk about elongation. So you have a stress, and there are 2 type of stresses. You have normal stress and you have a shear stress. Now, as we have discussed before, whenever you apply a force on a member, so this, I'm applying a tensile force, so I'm trying to stretch this member. So whenever you apply a force, you're going to see elongation. You're going to see a stretching of that member because now it's a deformable body mechanics. So now we cannot assume the body will remain rigid. We also have to figure out the elongations, how much the body is stretching because of this force. So actually, this is what will happen. The body will elongate by some amount if it's a tensile force. And if it's a compressive force, the body will compress a little bit. So we can calculate this stretching by the term we call elongation. So by definition, elongation is defined as change in length along the loading direction. And that's the formula for elongation. So for example, if you see this dog bone sample, so dog bone sample is basically a sample cut out from any material so that you can do some testing. So all we will focus is this part. So this was an original length of this testing sample is L naught. So if you apply a force, you put this dog bone sample in a machine and you apply a force. You try to like apply a tensile force, you try to stretch this member. So when you will apply the force, this member will elongate. So before the length was L naught, but when you apply a force, the member elongated and it goes to a different length, which is L1. So let's just say originally it was 10 inches of length, but when you apply a force, the total length becomes 12 inches. So how you can calculate the elongation is the difference between the two. So elongation would be 12 inches minus 10 inches is equal to 2 inches. So that's the elongation. So that's the formula for elongation. Basically, elongation is change in length, that is the final length minus the initial length. So whenever, so for example, in this case, let's just say it was 5 feet, and when you apply a force, the length increases to 6 feet. So what is the elongation? Elongation would be 6 minus 5, 1 feet. 1 feet would be the elongation. So that's how you can calculate the elongation, which is change in length along the loading direction. Now, from elongation, we can calculate strains. And strain is also a super important concept like stresses. We're going to be talking about stresses and strains all the time during this entire course. So strain is defined as change in length divided by the original length. And that's the formula for strain. So we know how to calculate the elongation. So if you divide the elongation with the original length, then the term you get is called strain. So the formula for strain is change in length divided by original length, or change in length is called elongation and divided by the original length. So in this case, the change in length was 2 inches in this example. And what is the original length? The original length was 10 inches. So if you calculate strain, the strain comes out to be 0.2. So in this example, if someone asks you to calculate strain, you're going to calculate the elongation, which is change in length, which is final length divided by what was the original length before applying the force. And then you can divide by the original length, and then you can calculate the strain. And this type of strain is called normal strain because this is coming out from the normal force. So there are two types of stresses. You have shear stress and then you have normal stress. Similarly, you have two types of strains as well. You have normal strain and you have a shear strain as well. Normal strain is because of the normal force and because of the normal stress, and shear strain is because of the shear stress and shear force. So what we have discussed here is a normal strain. Why it's normal? So let's just say this is a member. I'm going to draw 3-dimensional. So you apply the force F, and we can see this force is being applied perpendicular to the area. So if this is the cross-sectional area, the force is making 90-degree angle with the area. So this force is a normal force, and the stress which is going to be from this force is force divided by area is normal stress. So this is a normal force, and normal force is causing normal stress, and this normal stress is causing elongation. So because of this force, you will also have a stretching of this member. The member will elongate by some length. So if this was the original length, the member now will change the shape. It will increase in length because of the applied force, and this is the elongation. And if you divide elongation divided by this original length, you're going to get strain. And this strain is normal strain because it is coming out because of the normal force and because of the normal stress. So this type of strain is called normal strain. There's another type which is called shear strain. So let's see how we can calculate shear strain. So if that's the neon column which we drew before, now we're going to apply shear force. So if a force is applied parallel to the area, then this type of force is called shear force. So if this force is f of x, if this is x direction, if this is y direction, this is z direction, this is f of x, and the area is a of y because this is perpendicular to the y-axis. So if you calculate the stress in this case, force divided by area, then this force is called, this type of stress is called shear stress. And you can imagine how it will change the shape. It will not compress or stretch the element, but what this force will do is that it's going to kind of change the shape of the member. So that's what's going to happen. if you apply a shear force, you're going to have shear stresses in a member, and it will change the shape. It will not elongate or compress the member, it will change the shape. So because of the shear stresses, you're going to have changes in shape. So it's going to create an angular distortion. So it's going to create some angle of distortion. And we can visualize this by using a stress element. So what is a shear strain? So shear strain is basically a measure of angular distortion or change in shape when subjected to shear stress. So normal strain causes elongation, but shear strain will cause angular distortion. And you can visualize this by using a stress element. So for example, this is a stress element. I've drawn two-dimensional. So if you apply a force here, what you will see is that you will have a change in shape. So whenever you have a angular distortion, then this type of strains will be called shear strain. And shear strain can also be calculated by the same formula, change in length by original length. But in this case, the change in length is this length. So strain you can calculate by change in length over original length, but in this case, the change in length is this, u of x. And the original length is L naught. So there are two methods to see stress. One is a macro scale approach or an average stress approach, and there's another one which is called a micro scale approach. But there are two types of stresses. You have normal stress and then you have a shear stress. Normal stress is because of the force acting perpendicular to the area, and shear stress is because of the force which is acting parallel to the area. And similar to the stresses, you have two types of strains as well. One is normal strain and another one is a shear strain. So normal strain is gonna create elongation or compression because of the normal forces and stresses. And shear strain is gonna cause change in shape because it's acting in such a way that it causes changes in the shape. So if you wanna visualize again, if this is the column, that's the normal force, right? So it's going to create normal stresses and it's going to compress the member. And that's the shear force because it's acting parallel to the surface. So what shear force will do is that it will create distortion. So it will change the shape. So these are the two differences. So you have like normal stress, normal strain, shear stress, and shear strain. And that's the formula for shear strain. Now we know what stress is, what strain is. Now what we will do is that we'll try to calculate the relationship between stresses and strain. So we'll do an actual experiment. I think the guys who have like already taken material class, they have already like done this stress strain. Like, yeah, but for the rest of you guys, I think it's a new thing. So this is one of the simplest tests that can be performed on any material. So if you want to know the material properties, that when material will fail, how much it will elongate, what is the elastic strain, what is the plastic strain, and when it will fracture, you can do that by taking that material and carving it into this shape, which is called a dog bone shape. So basically what you can do is that you can take a part of the material. For example, if we want to know how steel behaves, when steel will fail, so we'll make a sample out of a steel and we'll put that sample into a machine. And what this machine will do is that it's going to keep on increasing the force. So when it will apply the force on that member, so the member will stretch. It will keep on increasing the force. Ultimately, the member will break. And then we can keep on calculating the stresses and strains, and then it will help us to understand the material properties of specific material we are talking about. So, for example, this is a sample made up of, let's just say, steel. So we'll put that sample in a machine and we'll keep on increasing the force. So when we'll apply a force on that sample, you can see it's going to increase in length by applying this force. And we know the force, we know the area, we can calculate stress divided force divided by area. We know how much elongation is happening, we know the original length, we can calculate the strains as well. So at every different point, we can calculate the stress and we can calculate the strain because we know how much force we are applying, and we also know all the other configurations to calculate the stresses and strains. So we're going to keep on increasing the force intensity and the material will keep on stretching. So the more force we will apply, the more this material will expand. And there, so if we keep on increasing the force, ultimately what will happen is that the material will break. So that's what this test does. If you want to know the material properties of steel, you put a sample of steel into the machine and you keep on increasing the force, and you're going to see the material stretching, and you're going to see stresses inside and strains inside, and they were going to keep on increasing, and ultimately there will come a point when this material will fail, the sample will fail, it will fracture. And we can see this visually by drawing a stress strain curve. So we know what stress is. Stress is force divided by area. We know what strain is, which is change in length over original length. We have this sample. It's made up of some material. Let's just say it's made up of steel. So we are interested how steel performs, how much stress steel can take, and when the steel material will fail. So we will make a sample out of steel material and we're going to put it in the machine. So what this machine will do is that this machine will apply a force and with increasing intensity. So we'll start the machine and the machine will keep on increasing the force on the material. So when it will increase the force, you're going to see elongation in this dog bone sample. And we can also calculate the stresses and we can also calculate the strains. So the material, the force will keep on increasing and we will keep on noting down the values of stresses and strain, and we'll keep on plotting this on this stress strain curve. So for a while, you will see kind of straight line. So you will keep on increasing the force. You will observe increase in stresses inside the dog bone sample, and you also will observe elongation. So you will also observe increase in strains. After some time, we are just increasing the force all the time. Like we're going to keep on increasing the force. So after some time, you're going to see a straight line. So you will observe a lot of strains, a lot of elongation, but you will not observe any increase in stress. That's what you observe when you do the dog bone sample test on a steel material. But we'll keep on increasing the force. So if you keep on increasing this force, so after some time, you will just keep on increasing this force and you will observe what's going to happen to this dog bone sample. So after some time, you're going to see increase in stresses and strains again. And at this point, you will start to observe that the cross-sectional area has started to shrink. We call this necking. So after some time, at this point, the cross-sectional area will start to reduce. So you're gonna see some necking. And if you keep on increasing the force even after you observe the necking, then you will see reduction in cross-sectional area, and ultimately the dog bone sample will break. So you will see a fracture. So different materials. So this stress strain curve is for a steel material, and every steel material will, if you, for a particular steel material, you will observe same type of stress strain curve. So for every material, you have a specific stress strain curve. So this is a signature of material. So you can know a lot about the specific material by plotting this stress strain curve. So there are some important things which you can note down. For example, if you think about this point, this is the maximum. This point is called yield point. Yield point, and the stress at that point is called yield stress. And till that point, all the strains are called elastic strains. So if you apply a force which will push the material beyond this point, so if you are increasing the forces and the stresses are also increasing, and if the stress goes beyond the yield point, and after that if you remove the force, the material will not go back to its original position. You will observe permanent strains, and you don't want that. So mostly what we do is that as engineers, we want we don't want stresses to exceed the yield stress. And yield stress is specific for every material. So for example, I think for steel, we already know what yield stress is. It's about 420 megapascal or something like that. For different materials, you have a specific yield stress. We already know that. So, and we can calculate the stresses. We can calculate external forces. We can calculate reactions. We can calculate internal forces. From internal forces, we can calculate the stresses. And we have to make sure that those stresses does not exceed this yield stress, because then we're going to have problem. We're going to have permanent deformation, and we don't want that. And also, this point is called fracture point. And maybe this stress is, let's just say, is 600 megapascal. So if you keep on increasing the force, it's going to keep on increasing stress. And if the stress increases to this point, then the material will fail, this particular material. So every material has a specific stress strain curve, and by looking at that stress strain curve, we can calculate like when this material will fail, at which particular stress level it will fail, at which particular stress level, if you go beyond that stress level, you're going to have permanent deformations. So these are the material properties which you can extract by using this simple test. And remember, in the first lecture, when we were talking about forces, we concluded that forces produces stresses, and stresses are responsible for the failure. So that's why we are calculating stresses. So after we know the forces, we can calculate stresses, and then we can compare these stresses with these yield stresses and failure stresses to figure out the material will fail or not. Or also we can calculate the forces from the stresses, so that we can know like that's the maximum force we can go after. If we go beyond that force, we're going to have problems. So for different materials, you have different stress strain curves. So for example, this is a stress strain curve for a steel material, the G50. This is a stress strain curve for copper. This is stress strain curve for aluminum and steel and bone. So different materials have different stress strain curves, and we can know a lot about that material by looking at the stress strain curve. For example, if we see this bone material, we can see this will fail at about 200 stress and it can only elongate to about 0.001. I mean, so if you have a bone, you put it in a machine, and the machine will apply a force, so it will fail early. It will fail around at 200 megapascal of stress, and it cannot elongate. It will just elongate a bit, and then it will fracture. But if you talk about copper, if you keep on applying force on copper, the copper will keep on stretching. So the copper can elongate a lot, but it cannot take a lot of force. So copper is still a weak material relatively, but it can have a lot of elongation. If you can apply a force, it's going to keep on elongating, and it's going to have a lot of strains, and then it will fail. If you talk about steel, this is the yield stress of steel, and the steel will fail somewhere here. So we know that the steel can elongate about 0.3, 30% of the original length before failure. And it can take about 370 megapascal of stress. So it can take a lot of force, because the more the force, the more the stress. So it's a relatively strong material. So you can also see from the figure that the bone is a brittle material, because it will not elongate a lot, it will just fail. But the copper and steel is a ductile material. So you can do a test and you can know a lot about material. And we know this information because we can calculate the forces and stresses, but we have to compare those stresses with the material properties so that we know that we are not applying more forces than the material can take. So I'm going to talk about Poisson ratio and Hooke's law, and then we'll do calculations from the next class. So let's talk about Poisson ratio a bit. So we know when we apply a force, we'll have elongation. But in addition to elongation, we also have something other in other directions. So you will have elongation along the force where you're applying, but you will also have reduction in the other directions. So if this was the original member and you apply the force, so what it will happen, it's gonna elongate where you have applied the force, but it's gonna reduce from the other direction. So that's what actually will happen. So if you stretch, you're gonna see elongation along the force where you're applying, but you're gonna, from the other uh, directions, you're gonna have reduction in shape. And you can calculate this by using this formula, and this is called Poisson ratio. So Poisson ratio is basically strains along the axis where force are applied and the other direction. So if this is strains in y direction and these are strains in x direction or strains in z direction, so if you divide the longitudinal strain with the transverse strain, then the ratio you get is called Poisson ratio. And this is also fixed for all the materials. We know Poisson ratios for all the materials. So if we know the Poisson ratio, and if we want to calculate the strain in one direction, we can also calculate the strains in other direction. And when we'll do the calculations, then it's going to get even simpler and even easier. But next time we're going to talk about Hooke's law, and then we'll do some calculations for the chapter.